So hello everyone. So in the previous session we have started the basics of calculus and we saw the intuition behind the calculus and we sort of tried to introduce the calculus in such a way so that you could reinvent those things yourself. If you were present at the time of Newton, at the time of Leibniz, and if you would have encountered the same problems and maybe you could have discovered these solutions by yourself and reinvented all those tools. So now we'll go further into our pursuit of learning the calculus from the perspective that we need to internalize these things. So in the previous session, if you have watched that, so there we discussed about uh, computing differential of different equations, like you had some function, for example, f of x, and you wanted to compute its derivative. So it was something like this. So let's suppose we had this x square. So we said differential of this is basically equal to 2x. So even we did not just have that rote sort of memory in which we told you to memorize this, but rather we derived all these concepts and we showed the visualizations what they mean. So now these functions can basically be they can be merged or combined in certain ways. So if you ask me how many ways are there in which I can combine these functions, so the first thing is there are three ways, I'll say. Three ways to combine these functions. So most of the times you will have these algebraic expressions, and sometimes you will have trigonometric functions like cos of x, d by dx of cos of x. You say this is equal to something d by dx sine x. So we have seen the derivation of these also. We have seen the derivation of these also, and now we'll see how to combine these. What are the different ways of combining these things? Okay, so let's get started with the combination. So I said there are three possible combinations, three possible types of combination which you can do. The first type of combination is that you can add or subtract these functions. You can add or subtract these functions. So for example, we have a function, we know it is f of x, let's suppose is sine of x. Okay, and let's suppose we have another function g of x, that is x square. So you can have a function h of x, which is addition or subtraction of both of these. So it can be sine of x plus x square. This is one type of function, how we can combine these functions. The first type is that we can have the addition or subtraction of functions. So here you can add more terms and they itself will be they will be functions themselves. So in the similar fashion, the second thing can be we can have the division or multiplication of these functions. So we can multiply or divide in a similar fashion like this. So we can have sine x multiplied by x square. This is basically f of x multiplied by g of x. F of x multiplied by g of x. Okay, and let's call it some h dash of x. The third possibility is that we can take composition of a function. We call it composition of a function. Composition of functions. So what's the meaning of composition? Let's spend some time to understand this composition of function, and then we'll say what this is. For example, let's suppose you have a function f of x that's equal to x square. Okay, then you have a function g of x that's, let's suppose, equal to some sine x. Okay, yeah, I just reversed the things here, but it's okay. So what if I have a value of, let's suppose, 2? So I am saying x is equal to 2. So you will first compute this f x, let's suppose. So you'll compute f x that's equal to 2 square, which is equal to 4. Okay, then on this 4 you will apply this input to the g of x. So you will say sine of 4. It will have some value. So what we are doing is, so first we are applying this function x square, and then we are applying this function sine of x. So we are having f of g of x like this. So we apply first f of x. So this is called as inner function, let's suppose, inner, and this is as outer function. This whole is an outer function. So this x takes the value and it gets into this function first. So this function squares the value of x. And in the second case, what we do is whatever is the output of this function, it gets input to this function. Okay, that's why it's called composition of functions. So you saw the loops. It's like that. So we have this g of f of x in here. So we can have the functions like this. So how can this h of x be written? H of x is equal now g of f of x. So this can be written as sine of x square. Okay, now this function, if you see, is actually this f of x, and outer function is g of x. So this is called as composition of function. So why am I basically telling you different types of different combination of these functions? Because so far we have learned how to differentiate the functions which are separate. I told you if you have, for example, x to the power cube, so d by dx of x to the power cube is equal to 3x square. So geometrically, you know what this means. Geometrically means if I slightly nudge this x cube, if I slightly nudge the value. So we had at least two intuitions that we saw. So let's suppose we have this. Let's suppose this is the value of x square. Graph of x square is like this. Okay. So what is the meaning of d by dx of x square? So the meaning is if I slightly nudge the value. So what is the change? What is the rate of change? So if I nudge the value, what's the rate of change? So another thing that I showed, and the visualization I showed you that in case of a square, for example, this x. So this represents x square. So area of this represents x square. So dA by dx here is the meaning of differentiation. So if you slightly nudge this x like this, so there will be a slight change in area. So there will be a slight change in area. So that's the meaning of this. Just revising you the thing. So what is the main geometric meaning? So you can see it graphically, or you can see it like this geometrically on some figures. If you have x square, x cube, and things like that. So now we have seen how to take care of these functions separately, like we have x to the power n or something like that. Then we have also seen trigonometric functions, sine of x, differential of d by dx of sine of x is cos x. Similarly, d by dx of cos x is minus sine x, and something like that. So now we want to combine them together, and we want to see what are the rules that we have to apply and how to basically differentiate these functions which are in combination. The first thing we will deal with is called as sum rule. I don't want you to memorize the rules. I just have a focus over here and see how I will derive these rules. So then you will internalize these things. Then you will understand these things. Okay, these are not some rules to memorize. So these basically are the things which we can derive on the fly. Okay. Then once you practice a lot, and then you automatically memorize these things as well. So let's suppose I have the function sine x, sine of x plus x square. This is my function. Now you saw we have two functions. Sine x is a separate function, and x square is a separate function. Now I basically need to see if I slightly made some change in this. If I slightly made a change in x, so what will be the change? Okay, that's my question. So if I made a slight change in this x, what will be the total impact of this? The first I'll introduce to you guys to a tool by which you can plot a function. So it's called a Desmos. You can go to online and just search Desmos calculator. There will be able to plot the functions. Okay, basically functions are nothing but they actually have plots. So they just take some input and give some output, and you can plot them as a function. So let me show you those things. So here is my Google Chrome, if you see. So I have already plotted some function. Let's suppose this is the function of x. X plus 2 is a straight line like this. So if you see it here, so you see the line over here. So you see the line over here. So this line represents basically this x plus 2 if you see it here. I just put the values on this, and then it will give me the curve of that. It will give me a line, or if I have to plot parabola. So you can plot it in Desmos. So let's suppose we have to plot x square. So x square basically means like this. We have to plot x square. This is the function x square. So here if you see, for example, you know that x square behaves like this. So if you have x, this will give value x square. So let me write it in red. So let's put 1. So it should give value 1. If you give value 2, it should give 4. It should 3, 9, and things like that. So you can see it over here. So for 1, if you see over here, the value of y is also 1, because this is how it touches the axis. So if you see the value 2, 2 is over here. If you see, okay, if you see 2 over here, so here the y value is 4. Similarly, if you take minus 1, it will be plus 1. So that's why it lies in the positive quadrant. If you see, it lies in positive half space. If you say it is the positive half space, because this function is always positive. So there is no question that it will go into here. So again, now you see that this is the function of x square. Is it clear?
Yes, sir.
This is called as parabola. These functions are called a parabola because they make parabola. Now what I'll do is I'll have a combination of these functions. Okay, I'll have a combination of these. I'll just add sine x plus, you see, the sine x separately looks like this. So if I just write sine x, so it looks like this. Sine of x. So sine of x is like this. This is the function of sine of x. So now I want to combine these two functions together. I want to combine the sine of x This function is like this, which you see on the screen like this, and you saw the parabola looks like this. So these are the two functions which I actually want to merge together, and I'll see what is the resultant function. So what will happen to the function? It will be a new function. So we have this f of x was our sine x. So f of x, this is our sine x, f of x, and then the earlier that we saw was, let's suppose, g of x, which is x square, a parabola. So if we now combine these functions, now I want to see how to differentiate these things. So just adding here f of x square, x square. So now you see this function. So it got a little bit, it went to a negative way. Here it is, the change in function. So it remained like x square, but still it went to that negative part as well. So there is, this is a total function. This function represents, if you see, it represents sine of x plus x square. Is it clear? So how I combine these functions in this and to show you the visualizations. Now what is the motto? Why did I show you this? Okay, coming back to the tab screen, and I'll show you what is the meaning of this. I'll just erase this. Okay, this is the function we are dealing with. So if you plot it separately, like sine will be something like this. Let's suppose we plot these things separately. So we'll have a sine curve, for example, like this. Okay, so if you have this curve of x square, it will be something like this. Let's suppose this is x square and this is our sine x. So these two, when combined, they produce that combined effect that you saw on the screen when I plotted it. So what is the meaning of this? If I want to differentiate this, sine x plus x square. So what's the meaning of this? The basic meaning is that we have to just create a small nudge onto this x. We want to see how does this x affect. So if I slightly change the value of x, so what will be the effect? So initially, if you see, let's suppose we'll see at 0.5. Let's suppose this is the value 0.5, 0.5. So if x, this is x, so this is x. So here, if you see the combination of values, if you want to take, this is sine of 0.5, this value. So this value is sine of 0.5. So this is 0.5 or x square, let's suppose. So there are two components to this. So the first is, this is sine, and here the second is for the x square. So this is 0.5 x square, and this value is sine of 0.5. Okay, now this is the combined value which we get. So over to this value basically represents this 0.5 whole square plus sine of 0.5. Do you agree with this?
Yes, sir.
Okay, so now what's the meaning of differentiation? If you see how we introduce differentiation, we see if we made a slight change in the dx, so what's the impact? Basically, we want to see the rate of change. We want to see how fast or how slow does the function change. So we'll do this thing. So we'll make change sine of 0.5 plus some dx, very slight change. Okay, and similarly with the x square, we'll say we have this 0.5 plus some slight dx whole square, and then we'll see what will happen to these things. So we are making some change over there. So that means, so we'll be taking values like this. We are making slight change on this red mean, and we are making some change, slight change over this. We're just shifting dx, but this is the dx. This value is dx. So we are slightly shifting it, and we want to see what is the effect of these things. So if you see now, so our f of x basically was equal to sine of x plus x square. This is our function. So what I told you, we want to see what is the change in the sine of x. So I can write it d sine of x. So that basically means change of sine x, and then I can write d of x square. That means, and I can here write for, let's suppose, df, change in f. So how does f change? F changes by changing this x. So x has an impact over the sine x, and x has a change in impact on this x square. That's why I wrote change in f is basically equal to change in sine x and change in x square. That's how I read this equation. Okay, now I know that because I know the derivative of sine x. So you know that what is the change in sine x? That's basically equal to cos x dx. Why? Because it depends over here. So here the change basically will be, if I made a slight change, this will be cos x, and this is the dx, the smallest portion that we do. That's why we are multiplying that, because we are taking that strip and we are finding its area, sort of thing. So cos x is basically its change, and we took a slight area, that's this dx, slight, that nudge. And plus we can write the x square in the similar fashion, because we have seen that previously. This is equal to 2x dx. That is our df. Okay, now this is equal to df is equal to, taking this dx as common from both the things, so I can write df by dx, that is change of f with respect to x. So if I made some change in x, so what will be the change in f? that will be given by cos x plus 2x. So if you see it, what I did is, so if I backtrack it, if I had a function, let's suppose f of x, some g of x and h of x were two functions. Here we had these sin x and cos x. So if you see, what we did is, so it's not just for this cos x, and I'll just compute it for generic function. So this is our f of x, let's suppose. So now what I said is, this df basically change in f, it is equal to change in g of x, okay, plus change in h of x. So now we have to differentiate this, okay, because now we have to when we do it, so it will be d by dx of gx plus d by dx of h of x, that's equal to df by dx. So this is our sum rule. What you have been taught in the school, or what you have been taught so far is, if you have some functions, let's say x square plus sin x, so you'll first differentiate this, then differentiate this. That's what we derived basically from this graph, if you see. So what we again, to reiterate the approach, we just made a slight change in d of x, and we saw that this is the change that will happen, and we saw change of f is basically equal to change of one function plus change of other function, that then we derived this. Is it clear?
Yes, sir.
This is called as sum rule. So here, if we have two functions in which we have a subtraction or a addition symbol, so you can directly write the sum rule. In words, you mean that differentiation of function, which is basically addition of subtraction of two functions. You differentiate them individually, okay, and add and subtract accordingly. So that's the first case we are dealing. We handle the first case. So we said that there are many ways to combine. There are three ways to combine functions. The first is this: how to differentiate this. You saw by using the sum rule. Now we'll see this multiply and divide thing. So how to take care of this? If we have if we have two functions which are multiplied together, so how to deal with this? Okay. So second thing is for this multiplication and division. If we have functions in which we multiply or divide, so we'll take case of the multiplication, and similar will happen for the division also. So let's suppose we have this function sin x, and we have this function x square. So and we multiplied them. Let's suppose this is our final function f of x. Let's call this g of x, and let's call this h of x. Now we want to see how to differentiate these functions. Again, the first thing is we'll resort back to the visualizations, and we'll see first what's the meaning of this, and then what to derive. Basically, what I'm saying is, if I made a slight change in this x, what will happen to this thing as a whole? Okay, you can also plot this function. Coming back to our tool, so we can go back and see what is the. So this is sin x multiplied by. So we'll write the multiplication. So this is the function. Okay, you saw how function changed. So if I just decrease the size, so I think this is the function. So this function over here, which you have, this function represents sin x multiplied by x square. Okay, so this is the function that represents this. Now we have to see what's the meaning of differentiation. Differentiation means that if you slightly change the thing, so how does it impact? Okay, so how, if we say value of, for example, sin of x, if you put this value and then multiply it by some value over there, and if you made a slight change, what is the rate of change? We want to see how fast does it decrease, or how fast does it increase, how fast it basically changes. That's our goal. So you tried with this tool. So its name is Desmos calculator, and you plot different functions and try to visualize these things. What do functions mean? And you can plot the function on this 2D because you can have one variable and the other variable. So but it will give you enough visualization so that you can internalize and you can think about these functions on your own. So you now know the function. Now the task is how to make, and if we change some slight change in x, if there is some slight change in x, what will be done with the overall function? So the best way to visualize it, the first thing is graphical, but it'll be a little bit messier. The best thing is visualize this as an area. If you have multiplication, visualize it in area. For this is square, it has length sin x, and it has x square of breadth, because length and breadth, the sides, let's suppose it's a rectangle, not just square. So it's a rectangle having sin x of length and x square breadth. So what I'm saying is, I'm saying if I slightly change x, so what will the change in area? So you know now this function basically represents area of the square. Area basically is equal to sin x multiplied by x square. So this is what area is there. So now I want to see what is the change in area if I change this x. That's represented by dA. So here it is represented by f, so we'll call it df. So what's the change in function? What's the change in area if I slightly change this value of x? If I again made it in a good manner, so we had something like this. So this here we represent this as sine x, and this is our x square. Now the area of this rectangle basically is the function that we have. Okay, so now if I slightly change this, if I slightly change dx, okay, slightly change this dx, so I'll increase the side, so what will be that, because I have to increase dx from here and dx from here, so what will be the change in area? Okay, that I want to show you. So here what will happen is I'll have a strip, the area will be added like this. No, sorry. So change in area will be something like this. This will happen from this side, and this side will also increase in area, and we'll have this strip as well. This will be our change in area. I just nudged, so here this value is equal to dx. So if you see, this to this is dx, and the slight area change basically. So here if you see, the whole of this is x square. Similarly, whole of this is sine x. This is dx. Here small area is dx and dx. Is this clear? So what I'm doing is I am slightly increasing the area, by d. If I am slightly increasing the sides by dx, so what will happen to that I'm showing you. Is it clear?
Yes, sir.
So if I have this, let's represent f is equal to area. So now we know this area is represented by sine x multiplied by x square, because that's a rectangle, that's the area of rectangle. I want to see df. Df means change in area. So I can write f is equal to sine x multiplied by x square. So what is df? Change in area. So if you see, change in area has three strips. The first strip is this one, this dx and sine x wala strip. Then we have this strip, dx x square strip. Then we have this strip. So we have three strips. So I'll call this strip 1, strip 2, and strip 3. Okay. So change in area will be 1 plus 2 plus 3. I'll have to add all the strips. The area of all the strips is the change in area, basically change in functions. So if you see area of the first strip, area of this strip, if you see the area of this, so this is the rectangle. So the area is equal to sine x dx. Okay, this is length, this is breadth. So sine x multiplied by dx plus, what is the area of second strip? X square dx. Okay, so the area. So if I have to like combine all the things together, I'll see. So change in area basically means, so this is our sine x and this is our, this is not just like dx. So here we will have, so the change in area, because it's x square, so it will be dx square basically. So where is it? Right here. So because this whole represents x square, so if you make a slight change in dx, so the change this will be, it will be dx square here. So what I did is I made a slight change in x, so because this whole represents this x square. So if I made some change dx, so the change in here will be dx square. So I'll have to put dx square over here. So dx square will be the change in area. Okay, because I slightly made x, and area change will be dx square over there. So similarly for this strip, if you see this is our x square, and now if you made this slight change in dx, so what will happen? So this side, this will become, this is x square, and this will become the slight or change in this d of x. So I'll say this is d of sine of x, let's suppose. So this will be slight change in sine of x. So this will be slight change in sine of x, because the whole side is represented by sine, and here it will remain x square. So in the similar fashion, here it remained x square, but this change was d of x square, because that's how this x square got changed. So the first change in first area is basically equal to this much, d of x multiplied by d of x square. Change second strip, if you see the second strip over here, the change in area is x square multiplied by d of sine x. Change second area, because dx it got changed from here and dx is got changed from here. So we can ignore this because it only includes the dx, and you know that this they tend to 0. So maybe there will be some something over here, but as dx approaches 0, this whole quantity becomes 0, this small strip becomes 0. So these are two major terms which will be there. So these are two major terms. So what I have now, I'll just rearrange these things. So change in f is basically equal to sine of x dx square, okay, plus x square d of sine x. This is what I have here. So now you know that what is the change in x square. We know that this is sine of x dot 2x dx. Okay, plus this x square is as it is. What is the change in sine of x? That's cos x dx. This is change in f. So df, taking this dx and dx common, so df by dx, and this will be equal to sine of x dot 2x or multiply with x plus x square cos x. This is called as product rule. Product rule. So there is no special thing with the sin x cos x. I can just now have these things. I can have g of x and h of x. So I'll have like this. So change in f will basically be equal to g of x multiplied by h of x. Okay. So d of h basically now, because we have to change in the second, plus uh, h of x dot d of g. Then I can just have di dx is equal to, keep the first function as it is, differentiate the second function, and keep the second function as it is, differentiate the first function. This was the rule that was taught to you when they told you, if we have two functions which are in which we are multiplying things together, then you will first differentiate the first function, keep the second function as it is, then plus differentiate the second function and keep the first function it is. This is the sum. This is the product rule. Product rule. Is it clear? Is the visualization also clear? You saw this visualization. Just keep this in mind. This visualization. So there are three strips if you see, and this strip gets ignored because dx squared basically tends to 0. It is basically 0. So area change in this, area change in this. This is equal to this. I just showed you a particular function of sin x, and you can easily derive this. So are you convinced about this? So we saw
Yes, sir.
two rules so far. The first rule was the sum rule. The second rule was product rule, and we handled these two cases. The first case that we handled was if we have to add or subtract, if we have functions in which we add or subtract functions. So how to handle the derivative. Similarly, multiply, divide, so you will use the product rule. The third, which is the most important and the backbone of deep learning's method called as back propagation, that we call as chain rule. Just giving the name upfront. So here the third case was if we have composition of functions. If we have something f of g of x, like we had this sine of x square. So x square itself is a function and sine x is a function. So we compose them together. So there we'll use chain rule. So I told you this is the backbone of back propagation. So there's an algorithm back propagation which you will learn in deep learning. So that time you must have an understanding of this chain rule, how this chain rule works. Okay. So now we'll say, let's suppose this new function. We'll not call this f(x). We have this is just for example. So we had this h of g of x. Let's suppose. So this is our f of x, composition of functions. So we had some function, let's suppose g of x, and this is f of x, and we combine them and we call it a composition of function. So this can be written as like the f of x is equal sine of x square. So this is our function that we have. Now we need to see if we differentiate this. So if we made a slight change in x, so what will be the change in this? And you can also visualize this function also. So you can visualize, go back to Desmos and just see that. So here you have, so we'll put this is sine x. So if you just add square, so here you have, this is our function f of x square. This is the function. So I hope you will play with this tool as to get some better understanding. This is the function. Now we need to see how basically we can take the derivative of these composed functions. For that we'll resort to a different visualization. So here I'll make three number line axes. This is, let's suppose, x. This represents x, this represents sine of x, and this represents sine of x square. Not the values but the line. For example, if I made some change in this, so let's suppose for this value of x we had the value of x over here, so we had the value of x square. So first we had x square, sorry, this is x square. So this was x, so x square will be obviously greater, it will be doubled, and then we have sine x will be value, for example, right here. So if this value is, let's suppose, 1, or let's suppose 2, so this will be 4. Okay, and this will be sine of 4 something, some 0 point something or something. So this will be some value. Okay, so if I want to make change in this value, if I do some change onto this, so if I do some change on this value of x, so if what I did is, so I just write these things. This is x square and sine of x square. So what is the meaning of differentiation? The meaning of differentiation is you make a slight change in the value of the input and see how is the function behave, what's the rate of change. Okay, so you made some change. For example, our x initially was here, the value let's suppose was here, and sine's value was let's suppose here. Now you did a change in x, so you made some change in x, and you see what is the impact of changing x onto this total. So first this will change, let's suppose. Now this is the change. So this change we want to capture. Okay, so this is the change that we want to capture. So we'll go from here to here, then from here to here, and we'll come up with the rules. So first thing, we'll have x, this will get converted into x square, then we'll be having this sine of x square. Okay, so now let's go back and see how to basically derive that formula. This is the formula of chain rules, okay, for the composition functions. So here we'll make a slight nudge. Let's suppose we'll call it dx. So we'll make a slight change in x. So if the x was here, we'll make a slight change. That we'll call as dx. Okay. Then what will happen to this? So what will happen to this is equal. This will happen. So it will be dx square. So this will be dx square. Because as x square change, so change in x square. So whatever happens, change in dx. So it will be change in dx. And similarly, we'll have this d of change in this sine of x square. So if we made some slight change in this x, so we'll call it dx, then that change will basically propagate, and this will become a change in x square, and this will be basically given by change of this x square. Let's take a simple value. Let's say if you see this like this, so this change in dx, you know that is equal to, this is equal to 2x dx. This is the change in x square that will happen. Let's call this dh. We'll call this dh. So here I can rewrite this equation now. This I can rewrite as d of sine of. Now you know that this x square has been changed to function h, so I can write h. Okay, so I know now change in sine of h is basically cos of h dh. Cos of h dh. I just changed this x square to h, and I similarly wrote it like this. Is it clear so far? This is basically cos of h, not cos of x, cos of h. Now I can just put the value of h. So you know the value of this h basically was put as x square, so I can write cos of x square. Okay, so now this is dh, not x dx. So cos of h dh is cos of x square. Now for the dh, I know that this is equal to dx square, or I can write 2x dx. So I can write it dx square or dx or 2x dx. So I can write this is equal to this. This is equal to cos of x square. Dx is basically now equal to dx square is equal to 2x dx. 2x dx. Is it clear?
Yes, sir.
So now if I want this was change in f, df. So that was change in f. So now I can write df by dx is basically equal to cos of x square dot 2x. So this is the value. Now for this example, we'll analyze it and we'll generalize this. What did we do? So what did we do basically is, the first thing is we change this x somehow. So that's what we did. So change in this x impacted this change in x square. So we had two functions. We have the outer and inner. So let's analyze this d by dx sine of x square. Okay, we had this whole, this is outer function, and we had this inner function. So if you just backtrack this whole thing, so what we did is, so we got this cos of x square. So what is cos of x? Is basically d of outer, change in outer, this. Okay, and then we got this 2x. So we got this, let's write it first and then we'll see. We got cos of x square dot 2x. So what we did is, this is d of, basically this is change in sine x, change in outer, change in whole outer. So we can write this as d of outer. This is multiplied by d of inner, because this is what got multiplied. So again coming back, so if we again generalize it, d by dx, if we have functions f of g of x, okay, we want to see it. So what did we do? So we did d of g, change in g by change in h, because we introduced that h ourselves. So we made this intermediary function as h, that this dx square we call it dh. So that's what I did, dg by dh, change in x, and then multiplied by d by dx of h of x. Is it right? Is it right so far? I understand the things
Yes,
what
sir.
I'm trying to do.
Yes, sir. Yes, sir.
Okay. So this is not just h of x. So here we have dg by dh h of, and here we have dh by dx of x. This is our another function x. So we call this as d of outer. So this much is d of outer, and this is d of inner. This is d of inner, d of outer. So how I can write it is like this. So I can simply now write it like this. I can say d by dx of this function is keep the hx as it is. So it can be written as dg or df of g, whatever you call it. So we'll write it like this. So this is clear. So I'll just have the notations which are clear. This is actually the rule, but I just wanted to make it simpler for you guys. So this is the rule basically that I want to introduce. So df by dx can be simply written as df by, let's suppose, dh multiplied by dh by dx. This is the rule actually that I want to write. This is called as chain rule. Because here if you have composition, I just introduced this h myself. Okay, so I introduced h. I saw what is the change of this function with respect to the previous x. So this portion here is the first one, that is the change in f, like this change in f with respect to dh. Okay, then going back in the second step, what I did is, what is, because I introduced a change in h divided by change in x. This will give me the change in total function divided by neg in f. This is what is called as chain rule. Is it clear?
Yes, sir.
So you have to peel these things, and if there are a lot of composition functions, for example, you have f, you have, for example, h of, g of, k of x. So now you have three levels. So you'll say something df by, let's suppose, dk by something else, and some other, there'll be three steps now. So you'll have to peel it one by one. And there's a famous quote by some professor: a chain rule is like peeling the onion. Okay, the more layers it have, the more you will cry. So for composition of two functions is sort of easy, but when you keep on adding more functions, you'll have to keep on introducing some other variables, like we introduced this h onto this in this middle step, and we kept on going. So is it clear? So now we saw this is differentiation in total. If you ask me, is it differentiation? Well, I'm done with differentiation from my side. Now you will just crumble these rules here and there, and you will just apply this onto these functions. So now you have requisites. If you learn any course on differentiation, you should be able to grasp the things. You should have the visualizations of this thing. Okay. So I don't think there is anything more to learn from the basic side. If you ask me, look, do I have some other things that I cannot grasp? I think this is the enough background. If you have understood this background, it will be easy for you to grab a book, to see a course online probably, and then start differentiating the equations. Now there'll be just combination of these. So if you have a difference, so I don't think I have left anything. Maybe there'll be some special functions which we have to take care for the exponential functions. What is the meaning of this? That you can take care. Okay, now we have seen if we combine the functions in for the addition, if we did the subtraction, if we did the multiplication and stuff like that. So and that way you can handle the differentiation. So for this sort, like, I can pause the discussion on the differentials here. So now I'll go to the optimizations. Is it clear so far? At least like 50-60% material, is it clear?
Yes, sir.